My name is Om Desai, and this is a project where we built and trained a model to predict the lineages of different SARS-CoV-2 viruses. If the COVID-19 virus eventually evolves new strains, then different vaccines will have to be used to combat each strain. This means that if we can find the lineage of a COVID-19 virus, we can make different vaccines to most effectively counter it. We used high-dimensional data that had over 12,680 attributes to build multiple models that had over 90% accuracy. The first of these models was a logistic regression model, which we used because it was good for predicting categorical data, like the region of origin of a COVID-19 virus. After that, we realized that there might be overfitting in the model. So we used a feature reduction algorithm to create a second logistic regression model that was able to slightly increase the accuracy and reduce overfitting. We also created a decision tree model so we could have an easily interpretable and visual model that shows us the most important predictors of the country of origin of a COVID-19 virus.
This is the output of the decision tree model shown in a visual format and given by our model. So you can see that it's built in a tree shape with more important nodes being near the top. So as you can see, whether there's a certain base at this one location can change a lot of the data, and this can help us find different bases that are very important in finding the country of origin of a certain genome of COVID-19. This means that we could identify specific genomes and be able to do it more easily based on the genomes that we see. To create the models, we used the Python programming language, and we mainly used the libraries BioPython, Matplotlib, NumPy, Pandas, and scikit-learn for our model. So the very first thing we did was download our data. And so we got our data, as I mentioned earlier, from the National Center of Biotechnology Information. Then, after that, we do our feature reduction model. And for feature reduction, we're using a lasso penalty. And so how that works is we're basically just using a cost function to try to make sure that as many of the values are 0. So that means that we're reducing a lot of unnecessary values. We then fit the data and we train the data so we can get both a training accuracy, a testing data, and a total amount of coefficients. Here you can see the results that are given when the Python code is run, and you can see multiple different outputs. Next, you'll see the accuracy here, and this basically just measures how well the model performed. So you can see that if the accuracy is high, like it is, the model performed well. Its predictions often matched up to reality 94.8% of the time. Next, this is a confusion matrix, and as I described earlier, it gives a more detailed overview of how the model performed. So you can see that 25 out of the 28 times it predicted that a coronavirus sample came from Asia. It was actually from Asia, but 3 out of those 28 times it was actually from North America, and the same general thing with the other 2. Next, this is the feature reduction data. And now you can see that the testing accuracy has decreased slightly from beforehand, but you'll also note that the training and testing accuracy are very close, which means there's not much chance of overfitting, and that there are only 11 coefficients, so it's a lot easier to understand and use.
Hi, my name is Siddhant Desai, and we will now talk about the purpose of our project, how the models we developed can be used, and its importance in the COVID-19 era.
Over the last 100 years or so, the US in particular has experienced 3 main major pandemics. That being COVID-19 in 2019, 2020, H1N1 in 2009, and the Spanish flu in 1918, I believe. And these are kind of some recent pandemics in our history. And through each pandemic, we have learned how to cope with them better and better. but we still need to learn how to deal with it more effectively and to kind of save as many people as we can. So to deal with these pandemics, what we need is information. And sometimes when there isn't proper information available, our leaders make lamentable or ill-advised decisions that sometimes aren't at the best of benefits. So we're going to look at two main pieces of information. And the information we're going to get is from something called genomic sequencing of the SARS-CoV-2 and other viruses. So genomic sequencing is basically looking at looking at the identity of a virus and understanding different aspects of it. And SARS-CoV-2 is the virus that causes the disease COVID-19. So the two pieces of information we can get from genomic sequencing are determining the country of origin from the virus and identifying and distinguishing between various strains of SARS-CoV-2. So first, let's look at origin. So determining the origin has many uses, right? First, we can have stricter border closures or policies towards countries of origin. So if we know where the virus is mainly coming from, we can determine how to deal with and how to close our borders accordingly. But this can also have some negatives, and that being we could kind of induce a stigma about certain group of people and maybe lead to isolationism. So this information has to be put in the right hands. The second would be to understand strain mutation. And with any virus, it's very possible that the virus mutates into multiple strains. And these strains may differ by different regions or from year to year, very similar to the flu. If you didn't know, the flu, we have to take a flu vaccine every year because the flu virus mutates every year and the vaccine won't work for the previous flu. The same way, there's different flu vaccines for different regions of the world. So the US's flu vaccine may be different than Asia. And identifying these different strains help formulate the most effective vaccine for each different strain in each different region.
Thank you to all my mentors and teammates. It was a great experience working with you all. Together, we've built a promising prototype that has a lot of future potential. Thank you all for listening to our presentation.